Hello everyone and welcome to this part of the lecture. So before we get into deep learning and other types of machine learning, we need to do an introduction to statistical learning, understand essentially uh, how data can be used to test the hypothesis, and then how the data can be used as evidence to confirm a given hypothesis for a relationship between input and output, and this how then see how this will guide us into building machine learning models. So the foundation for what we're doing here is what we call Bayesian learning. So Bayesian learning essentially calculates the probability that a given hypothesis, you have a set of hypotheses, and Bayesian learning calculates a probability that given this data, which one is more likely to be the correct hypothesis, and then make predictions on that basis. Okay, so essentially, Bayesian updating looks at learning as the probability distribution over the hypothesis space. So each hypothesis has a given probability of being true, and then we're interested in the hypothesis with the highest probability. So given the J's observation in the data, dj gives the outcome of random variable big Dj, and then we have a set of data points d1 all the way to dn. So given the data so far, these n data points, each hypothesis will have a posterior probability that, we have a prior probability, then we adjust the posterior based on the observed data. And the probability of the data given the hypothesis is called the likelihood. So predictions then use a likelihood weighted average over all the hypotheses. So we don't just make a prediction based on one hypothesis, but instead we make a weighted prediction based on the predictions from all the different hypotheses. So in this case, then we say that the big set D represents all the data, now including the unobserved data, and little d then is just a subset of this large set that has been observed up to a given point. And then, like we said, the key quantity in this approach, Bayesian learning, is the hypothesis prior, which is in this equation big P of hi. And the likelihood of the data under each hypothesis, which is big P of the data given the hypothesis hi. So if we apply Bayesian rules, then we are able to get the posterior probability, which is the probability of hi given the data D. Now, like I said, once we calculate all these posterior probability, then we can use a weight to get a final prediction by averaging each probability, each prediction from each hypothesis based on its posterior probability. So this equation right there shows that predictions are weighted averages over the predictions of the individual hypotheses, where the weights are the posterior probability P of hi given the data. Okay. So the better the hypothesis fits the data that we just observed, the higher its weight, and vice versa. The smaller, the worse the fit, the lower the weight of the given probability. So let's give an example to see how this works. Let's say, for example, that our favorite surprise candy comes in two flavors, cherry and lime. The manufacturer has a peculiar sense of humor and wraps each piece of candy in the same wrapper that hides the candy. So we don't know what type of candy we have before we actually open the wrapper. The candy is sold in very large bags, as you can see here, of which there are known to be 5 kinds. So there are essentially 5 hypotheses. Now we're trying to see what type of bag most likely we have. Okay, so we bought one bag out of these 5 types of bags, which are our hypotheses here. And from the outside, we can't really tell the difference because the wrappers are opaque. We can't really see inside of them. So hypothesis number 1 here is 100% cherry. Hypothesis 2 is 75% cherry and 25% lime. 3 is 50-50 between cherry and lime. 4 has 25% cherry and 75% lime. And then finally, hypothesis 5 is 100% lime. So given a new bag of candy, the random variable big H, which is hypothesis, denotes the type of bag. Which bag did we end up with possible values, obviously, from H1 to H5. Now, big H is not directly observable, of course. We can't really know ahead of time before we start opening the bag and unwrapping candy after candy, what type of bag do we have. So as the pieces of candies are opened and inspected, then the data becomes revealed, which is, in that case, we call that D1, D2, all the way to Dn. Okay, so in that case, the value of the data points we're looking at is either cherry or lime. So we can code that as 1 or 0, for example. Now, the basic task faced by our machine learning agent here is to predict the flavor of the next piece of candy. Now, as you can see, in order to predict the flavor of the next piece of candy, we have to consider the likelihood that our bag is one of these 5 bags based on the number of candies we opened so far. Okay, so as you can see, this scenario is essentially what we're doing here with Bayesian learning, even though it's very simple, but it essentially represents what we're trying to do here. So let's assume that we have a prior distribution, okay, from our experiment with this manufacturer. For example, the prior probability of a red bag is 0.1. The probability that it's H2 is 0.2 and 0.4, for example, 0.2, and then the whole lime bag is also very rare with a probability of 0.1. Okay, so we start pulling up data point candy after candy, unwrapping them. So that gives us the D1 through Dn. And every time we unwrap a candy, we update our posterior probability for each one of the 5 hypotheses. Okay, and then once we updated the posterior probability with this equation, then we can calculate the probability that the next candy will be cherry or will be lime using the weights we just generated. So if you look at what we end up with here, this essentially would be the posterior probability as we are picking the candies. Notice that in this case, we only picked lime candies. So naturally, you would predict our agent to increase the probability that our bag is full of lime, right? Or if not, then it's maybe this one. Okay, but it's definitely not this one. This one should die out fairly quickly because it's all red. So you can see that after the first candy is picked, the probability of the whole red bag is 0, which is normal. Okay, and then the probability of the whole lime starts getting confirmed over and over. So this example shows that Bayesian prediction eventually agrees with the true hypothesis And this is a characteristics of Bayesian learning, actually. So for any fixed prior that does not rule out the true hypothesis, the posterior probability of any false hypothesis will eventually go to zero. So as you can see here, the hypothesis that the bag is full of red candies went to zero fairly quickly. And the other hypothesis, the green one, also went to zero, which is majority red, and the blue one, which started with the highest prior probability at 0.4, eventually decayed to zero by the time we got our 10 candy from the bag. So more important is that the Bayesian prediction is optimal. So whether the data set is large or small, it doesn't really affect the accuracy of the prediction of the Bayesian model here. Given the hypothesis prior, any other prediction is expected to be correct less often. So you would definitely want to go with a Bayesian prediction. Now, the downside for Bayesian learning is that in real life problem, we have a lot more than 5 hypotheses to test. So imagine, for example, you're building a regression model. In that case, you have an infinite number of hypotheses because you have an infinite number of equations you can fit to the data. So the hypothesis space in reality is usually very large, or most of the time infinite. So we have to somehow use approximate methods then to adapt the Bayesian learning approach to real life situation. To conclude this example, as you can see here, the probability that the next candy is lime gets to almost close to 100% by the time you picked your 10th candy, because the model learns that most probably the bag you're having is full of lime candies. So a very common approximation is to make predictions based on a single most probable hypothesis. So instead of getting the weighted average of the predictions from all the hypotheses, we just select the most probable hypothesis and use it to make our predictions. So essentially, we take the hypothesis that maximizes the posterior probability P of hi given the data. So this is called maximum a posteriori, which is MAP, essentially, hypothesis. Okay, so it essentially chooses the hypothesis that maximizes the posterior probability. So predictions made according to this approximation are approximately Bayesian. Okay, so in our candy example here, the correct hypothesis H5 is picked after candy number 3, and as you can see here, starting this point forward, all of our predictions will be made using the blue line. So if we did this approach, this is where we would start using the correct hypothesis. As more data arrive, the two methods, the correct Bayesian prediction and the map Bayesian prediction, become similar to each other, closer and closer, because the wrong hypotheses will become less and less probable and will have a lower weight in the full Bayesian prediction equation. So finding the map hypothesis is much easier than Bayesian learning, just because you're only required to solve an optimization problem, which is essentially maximize the posterior probability, rather than a large summation over all possible hypotheses. Okay, let's stop here and continue the next part.